Okay, so just rewriting our dx f d big X equation again. I can multiply both equations on the left by f inverse, right? And so then I get basically I've just inverted that equation, right? So now I have an equation that's d big X is f inverse times d little x, right? Whenever you multiply equations, right, multiplying equations by matrices or second order tensors is a little bit different than multiplying by scalars, right? When you multiply, we all know you have an equation and you can rearrange an equation by multiply, it doesn't change the equation to multiply by something, right? And if it's a scalar, it doesn't matter if you multiply on the left or the right, it doesn't matter. But if it's a matrix, which is f is a matrix in this case, then you have to multiply on the same side, right? So if you can multiply on the left or the right, but you have to do it consistently, right? So if I'm going to multiply the left side of the equation on the left by f inverse, then I have to multiply the right side of the equation on the left by f inverse. Like what works the other way if you multiply on the right, right? But if you have any matrix times its inverse, f inverse times f is what? The identity matrix, and so it goes away, and that's how I invert that equation. All right, so we're going to use that to come up with another definition. Remember, we have ds squared minus ds squared. This time, and that remember that was dx transpose dx minus d big X transpose times d big X, right? And now we're going to plug in for d, before we plugged in for d little x, now we're going to substitute in for d big X using this new equation, right? Or just the inverse equation. So now we have d little x transpose d little x minus f inverse d little x transpose f inverse d little x and same rules apply. Like if we can distribute the transpose, it works the same way. We distribute the transpose, but now we have inverse transpose. And then we flip the order, right? But I'm going to go ahead and, well, I'll just write it out. So now we have dx transpose f inverse transpose times f inverse times dx. And then we can factor out the d little x. So d little x transpose times the identity matrix minus f inverse transpose times f inverse times dx. All right. And this thing we're going to label 2 little e, right? And so that leads to an equation for e 1/2 I minus f inverse transpose f, right? And this we call the Eulerian or sometimes you'll see it as Almansi strain, right? So, and the difference is before we were referring to vectors, we put everything in terms of vectors in the reference configuration. Now we put everything in terms of vectors in the current configuration. But what's on the left side of the equation is equivalent, right? ds squared minus ds squared. It's just what we did on the right is different. So let's see what that definition of strain looks like. If we plug in, remember, remember again, we have F is equal to I plus grad U transpose, right? So let's plug that into our definition of strain, E for the Eulerian strain. Gosh dang it. E is equal to 1/2 I minus F inverse transpose F inverse. That's equal to 1/2 I guess let me do this. Let me do it on time. Okay. Let me just point out that, if we go back to our potatoes, we have the reference and the deformed. So if we have a point X, and a point little x over here, before we wrote U here as, a function of x1, x2, x3. But that same U we can write, if we just drew the vector the other way, then we could write it in terms, because it was referenced to the current configuration, can write it like that. And so I guess let's not, I'm going to erase this because it's not relevant to what we're doing here. Let's go back over here and remember, okay, so we can write x is equal to little x plus u, where u is x1, x2, x3, right? So before we wrote it the other way, right? We said little x is equal to big X plus u, where u is reference to the reference configuration, big X components, right? So now we're just writing that equation the other way. We're writing this in terms of this vector and that vector, right? Okay. Well, now let's take a derivative with respect to little x on both sides of the equation.
Professor, just trying to make clear, that's missing a -1, right? That the Eulerian definition, I minus F minus transpose.
Yes. -1, right? Yeah, I wrote it here.
Yes.
Yeah, a second. Okay. So now I have this equation. I'm just writing x in terms of things in the current configuration. So little x, take the vector little x plus this u, which is defined as a function of, or referred to the current configuration. And then I'm going to take the derivative of both sides of the equation with respect to little x. I should probably do this in additional notation to be precise, but because this term looks funny. Okay, but basically, remember earlier we derived an equation that said f is equal to partial xi partial xj? Remember, we did that here. Right? And the way we derive that is just by writing, we just wrote little x in terms of big X and u of big X, right? So now we have partial big X, partial little x. What is that? This is partial little x, partial big X. What is this? Huh? Yeah. So this is F inverse, right? This is the identity matrix, and this is grad little x u, right? Okay, so then ultimately I have the equation F inverse is equal to the identity matrix plus grad little x u. Okay, so now I have an equation in terms of the gradient of x, or a gradient of x, a gradient of u, for F inverse. And so I'm going to plug it back into our equation up there for the strain. So 1/2 gradient little x u plus gradient little x u transpose plus gradient little x u transpose times gradient little x u. All right, and again, if we linearize it, right, so if this term goes to 0, then we have 1/2 gradient little x u plus gradient little x u transpose, or in additional notation, this is partial ui partial little xj plus partial uj partial little xi. Okay. And so that is the linear strain, linearized Eulerian strain, okay? And you see it looks exactly like the linearized Lagrangian strain, right? Well, essentially what we're doing, right, is we're saying that, ultimately we have this equation, right? We have x is equal to, big X plus u of x, right? Well, if u is very small, very small, then essentially we have that little x is equal to big X, right? So another way of looking is that the linearized strain makes no distinction between the reference and the current configuration, right? They're one and the same because u is small. Right? So next class, what we'll do is we're going to derive the small strain just based on completely geometric arguments. We're going to look at a cube, and we're going to look at how it might deform, and then we're going to write down the components. And what you'll see under small deformations, then you can make geometric arguments and get the linearized strain. Right? And what we'll see later is that, again, remember what I said in the last class, that there's infinite arbitrary definitions of strain, right? Engineering strain is referenced to the original length. Another way you might think about that is the engineering strain is referenced to the reference length, reference configuration, right? So the engineering strain in one dimension is sort of like the Lagrangian strain, because it's referenced to the reference configuration, d big X, right? It's in analogy with the engineering strain, right? So it's a change in length divided by original length, right? The Eulerian strain is in the current configuration. So it's more like the logarithmic or, true strain, right? It's referenced to the final length, right? The current configuration. So the change in length over the final length. So this is where we get these different definitions, and what we'll learn, later in the class is each of these definitions of strain have an energy conjugate stress measure, right? So remember from undergraduate mechanics or whatever, or geomechanics, stress is like a force divided by an area. But what area? The reference area or the current area? And so depending on how you define your strain, you'll have an energy or work conjugate measure of stress, right? And so it doesn't matter what strain you use, but you have to be consistent, right? You have to, if you're going to use a Lagrangian strain, you have to use the appropriate energy conjugate stress measure, and we'll see what those are when we get to them in a couple of weeks. All right? I think I'll stop there.